Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to continue telling you about projective geometry and in particular, tell you about the quadric surface. Now this quadric surface is the simplest kind of projective surface to study after the projective plane. And there are many ways to motivate it, but the easiest way perhaps is to consider what we do in affine geometry. How do we form the affine plane? Well, one way to think of it is we just take the Cartesian product of the affine line with the affine line, and hence we get the affine plane. So that suggests that, well, why can't we just look at the Cartesian product of the projective line with a projective line over some algebraically closed field F and ask ourselves, what type of geometric object is that? Okay. Well, the first thing to note is that, well, how did we construct the projective line? We constructed it using the manifold approach by gluing two copies of the affine line. So that's how we constructed it on open patches using the affine line. So since this consists of two copies of the affine line glued together, and the same with the second projective line, you can form this geometric object using 4 copies of the affine plane. So certainly this is an interesting geometric object. But if you define it that way, it's not clear that it's necessarily a projective variety. So that's the question I want to pose first, okay? This P1 cross P1, is it a projective variety? In other words, can you define it as the solutions to some polynomial equations inside some projective space? And the answer is yes, and let me show you how to get that answer. Okay, so to get that answer, we need to introduce an auxiliary set, a set that I'll call S, and it's going to be a subset of 2 by 2 matrices with entries in the field F. And the matrices that I'm going to pick out are precisely the ones that have rank 1. Okay, so of course it's a 2 by 2 matrix, so the rank of an arbitrary 2 by 2 matrix can be either 0, 1, or 2, and we want just the ones of rank 1. So what's another way of writing this condition? Okay, well, which ones are the ones of rank 0? Okay, that's only the 0 matrix, so we don't want that. And then if we don't talk about the ones of rank 0, we have to throw away the ones of rank 2, which are just the invertible matrices. So another way to write this condition is to say it's not rank 0, so it's not 0, and it's not rank 2, so that means that the determinant of this matrix has to be 0. And the reason why this will be important is that this set now is defined via some equation. Okay. So now what we want to do is we want to identify this P1 cross P1 somehow as a projective variety inside some projective space, and in fact it will be P3. And the way I will do it as follows, I'm going to go via this intermediate object here. So what's this intermediate object? It's this set of rank 1 2 by 2 matrices. And of course, you can scale any rank 1 2 by 2 matrix by a scalar, and it will still be rank 1. So this F cross, this multiplicative group of the field, acts on this set, and we can have a look at the orbits of this. So let's now pick a point inside our P1 cross P1. So we can pick it out using homogeneous coordinates. So the point inside here is given by x0 colon x1. That's the homogeneous coordinate there. And the point here is y0 colon y1. And what I want to do is to map it to some 2 by 2 matrix, which is rank 1. And what's that? All I do is I form the matrix product x0, x1 times y0, y1. Okay, so this is a 2 by 2 matrix, and let's just note some features about it. So firstly, this 2 by 2 matrix, it has a kernel which is the same as the kernel of this matrix here. And the image is just given by the span of this vector here. So note, these are not both 0 since they come as homogeneous coordinates. So this is a non-zero vector. And the span of this is precisely the image of this matrix here. So since that's one-dimensional, this has rank 1. So this is a rank 1 matrix. It's also not 0 because this is not the 0 vector and this is not the 0 vector. Okay, so that gives us a map from here, from these four numbers x0, x1, y0, y1 to the set S here, but we have to check that it induces a map from P1 cross P1 to this quotient here. So remember, this is only defined up to scalar. So we could have changed these numbers by a scalar, and that scales this vector here. We could have changed these coordinates by a different scalar, and that would change this vector here by a scalar. And the sum total at the end of the day just scales this rank 1 matrix. So even though it will change this element of S, it won't change the orbit it lies in. So this is actually a well-defined map from here to here. Okay, so the other thing that's rather interesting is that this map is actually an isomorphism. And that requires a little bit of thought, but it's actually not difficult to see why that's true. So what's the inverse map given by? So if you have any rank 1 2x2 matrix, how do you go back and get these two homogeneous coordinates? So the way is as follows. It's rank 1, so the image is one-dimensional. So since the image is one-dimensional, you just pick a basis vector for that image, and that will give you the homogeneous coordinates of this x0, x1 here. Also, by the rank nullity theorem, the kernel is one-dimensional, and that tells you what vector you should put here by picking this so that it has the correct kernel. And these are all defined only up to scalar, and that gives you the inverse map. So rather nicely, we've now written out all the points inside here in quite a different way as F cross orbits in this set of rank 1 matrices. Okay. So how does that give us our map to P3? Now we have to have a map from here to P3. So the key point is that this is a set of 2x2 matrices, so that means it has 4 entries, A11, A12, A21, and A22. So all we need to do is to write out those 4 entries in a row, and it's up to us what order we pick them in. So here I've just picked them in a fairly obvious order that I've written down here. So this matrix, of course, was only determined up to the F cross orbit. But of course, these are homogeneous coordinates, so changing this by a scalar does not change the corresponding point in the projective space. And so what we find is that P1 cross P1 now embeds inside P3 via this composite map here. And so the interesting thing to try to work out is, well, what's the image inside here? What is that image? Okay? And so the thing we need to ask is that image defined by polynomial equations? And that gives us our next theorem. In fact, it is. Okay? So P1 cross P1 is a projective variety. I'll denote it by Q. It's called the quadric surface, so that's why I've used the letter Q. And it's in fact given by the polynomial, homogeneous polynomial of degree 2, Z0, Z3 minus Z1, Z2. So why is that true? So what you have to realize is that, well, what is the image? The main thing is that you're not looking at all 2x2 matrices here. If you're looking at all 2x2 matrices, you get all of P3. You're only looking at the rank 1 ones. Okay? So to look at the rank 1 ones, firstly we omit 0, which is good because the 0 cannot be the homogeneous coordinate for a point inside P3. So we threw that out. The other thing is that we only want rank 1, not rank 2, so it's just this determinant condition here that we're interested in once we've thrown out that 0. So what is the determinant condition? Okay, what's the determinant of this matrix here? Well, it's A11 times A22, so that was our Z0 coordinate is here. That's our Z3, so that's Z0, Z3. And then we subtract A12 times A21, which is Z1 times Z2. Z1 times Z2. So this equation here can be just thought of as just the determinant equals 0 condition. And the key point is that this is just a homogeneous degree 2 polynomial in the coordinates for P3 that I had, Z0, Z1, Z2, and Z3. And that's called the quadric surface. So this is a very, very beautiful result, and it means that we don't have to set up some different theory for P1 cross P1. It's part of projective geometry because it is a projective variety inside P3. What is also very nice, and it's a little bit harder to show, is that there's a converse type result. So if you have any homogeneous degree 2 polynomial in Z1, Z2, Z3, and Z0, that defines some projective variety inside P3. And in general, you will find that that turns out to be isomorphic to this quadric surface. And in fact, the condition that you just have to check is that it's called non-singular. In other words, it's a smooth surface. It doesn't have singularities. Okay. So the important point is that there is a converse type result, and it doesn't hold all the time. For example, if you pick Z0, Z3 as your homogeneous degree 2 polynomial, then the variety corresponding to that is the union of the plane Z0 equals 0 and Z3 equals 0. But in that case, you get a singular surface. So if you get a non-singular surface, then it will be isomorphic to this one here. Okay, so we have this rather interesting surface that we can view in two different ways, this way and this way. And you might want to do some geometry on it. So let's try to do a bit of geometry on it, okay? And the first thing you might want to have a look at are the lines on this quadric cube. Well, there's some very obvious lines floating around because it is just P1 cross P1. So for example, we can fix a point of P1 like this 0, 1, and let the other point here vary across this P1. Okay, so this is P1 cross P1, and this gives us a copy of P1, so that's a projective line inside this quadric surface. Similarly, what we can do is we can fix the other coordinate, 0, 1, and vary the other coordinate over all of P1 to get you another projective line. And of course, the point of intersection is just 0, 1, 0, 1. Okay, that's the point of intersection. So what's interesting now, though, to see is, well, in what sense are these projective varieties inside P3? So that's the next question what we want to see. This Q is inside P3, so these projective lines are also inside P3. And how is that the case? Okay, so to figure out how these two lines occur as projective varieties inside P3, we have to remind ourselves how our notation worked. And the key point was the following. Inside P3, we had the homogeneous coordinates Z0, Z1, Z2, Z3. And how was it related to the homogeneous coordinates that we put on the P1 cross P1 using the x0, x1 as one homogeneous coordinate and y0, y1? Well, if you use the matrix notation, which is the most convenient, remember it worked as follows. So corresponding to the pair of homogeneous coordinates, we form this 2 by 2 matrix. And the 2 by 2 matrix with these entries corresponding to the point on the projective space, Z0, Z1, Z2, Z3. So we have this equality here, and expanding this out, we get this here, which tells us the relationship is Z0 equals X0, Y0, Z1 equals X0, Y1, and so forth. Okay, so let's have a look at some equations that we get, some varieties when you intersect this quadric with this value here. Okay, so suppose you have Z0 equals 0. Okay, so what's that? If Z0 equals 0, you have X0 equals 0 and Y0 equals 0, these two. So what's X0 equals 0? Of course, the X0 was the coordinate here, so you've basically got the point 0, 1, and you can make the Y0 and Y1 whatever you like, so it ranges over all of the projective line here. So you have this here. But you also have the points where Y0 equals 0. So you have P1 cross 0, 1 as well. So here the Y0 coordinate is 0. So that means that when you set Z0 equals 0, and also this equation which defines the quadric surface, you get not just a single line, but you get both these lines here. Okay, so let's keep going. What happens if we now set Z1 equal to 0? Then this term here equals 0. So both X0 equals 0 and Y1 equals 0. So again, the X0 equals 0 gives you this 0, 1 cross P1. But the Y1 equals 0 means that this coordinate here has to have a 0 here. So you've got P1 cross 1, 0. So that means that this line is still here, 0, 1 cross P1. That's this one here. But instead of having this horizontal line, this has changed. So that instead of the Y0 being 0, the Y1 is 0. So this has moved to a different, so to speak, parallel line. Okay? So one of them is like this, and the other one is slightly different. And the key point is that if you intersect these two crossed lines, what you get is this line here, just the one line. So of course, if you want both those equations to hold, so you have two equations like this, you get the single line, 0, 1 cross P1, and that is the line that gives you this one here. That's the equation that gives you that line. So what's interesting in this case here is that to define a line inside the quadric surface this way, you need two equations. You need both Z0 and Z1. But of course, it is given by equations, and in a fairly simple way. So now we have this quadric surface Q, and a very natural question to ask is there any relationship between this Q and the projective plane P2? Now, one of the reasons why you might suspect that there's a relationship is, remember, inside the projective plane you can look at lines and conics, and it turns out that all conics are actually isomorphic to the projective line. A conic is defined by a degree 2 homogeneous polynomial, and the same is true of the quadric surface. So you might think, why don't I just repeat that argument there and see whether there's some sort of relationship between the quadric surface and the projective plane. And in fact, you might be tempted to think that they should be isomorphic, but in fact, there's a lot more interesting geometry that appears when you look in this two-dimensional situation as opposed to the one-dimensional situation. Okay, so let's just recall how that proof worked. Okay, how do you map from a conic to the projective line? The basic idea was as follows. You pick a point firstly on the conic, so we'll do the same thing here. We'll pick a point on our quadric surface. Let's suppose it's just the one with coordinates 0, 1 and 0, 1. So that's this point that we had here, P0. And what you basically do is you look at lines through that point and see how they intersect the conic in that one-dimensional case. So we'll do it with the quadric here. Okay, so we're inside the projective space, P3, and we'll look at the set of all lines in P3 through P0. And of course, as before, you'll find that this is just isomorphic to the projective plane. So now we want to construct a map from our quadric surface to this set here. And it's quite easy to do that. Okay, we can use the same formula that we had before. We just map a point P to the line P, P0. Okay, so everything looks like it works just as in that one-dimensional situation. But let me show you two problems that arise which didn't arise before. So the first point is that the map phi here is not one-to-one. It's no longer injective. And the easiest way to do that is to pick a point P lying on a line like P1 cross 0, 1. So a line through this point P0. Okay, so this contains this point here. So this one here, P1 cross 0, 1. Let's pick any point on this line, say this one here. So where does it get sent to? It gets sent to the line P0, which is just this line here. And you can change this point as you like, and the point it gets mapped to over here is the same line. However you change this, you'll always get the same line P0. So that's non-injectivity. And the reason why it happens here, but not in the one-dimensional example, is that you actually have a line through this P0 which sits in your surface. In the case of a conic, of course, it's just one-dimensional, so you can't have a line as being wholly contained inside that conic, especially since we defined our conics to be non-degenerate. Now, there's a similar thing which happens here. If you pick the point P here to be on this line, it doesn't matter which point on this line you pick. The line P0 is just this line. So all these points will get mapped to the same line. So that means that this map is not injective. So there's also another problem that arises, which in fact is a lot more interesting, and that is the map here, P to line P0, is not even well defined. And why is that the case? So remember, there was a very special situation that occurred in defining this map in the case of the conic. What happens when P equals P0? Then, of course, what you did was you looked at basically two copies of P0, and you interpreted that as the limit as P goes to P0. So you have a tangent line. So you have a tangent line to the conic. Here you have a quadric surface. So at any point, you have an infinity of tangent lines. So now when you write this down, which tangent line do you send it to? Well, the point is that there's no natural choice at all. So this is not well defined. The map here from P to this tangent line is now, so to speak, 1 to infinity. It's multi-valued. You can pick any of these tangent lines that you like. Okay? So that's rather curious fact that happens in this situation here, is that this is not well defined. But what's very interesting is that what is this set of all these tangent lines? Well, the thing is that you're basically looking at a one-dimensional subspace, that tangent line, inside this two-dimensional tangent space. So the set of all these is actually just a projective line itself. Okay, so there are two problems that we have with trying to repeat the argument that the conic is isomorphic to the projective line in this case here. But nevertheless, if we throw away all the bad points where this phenomena happens and this phenomena happens, it actually turns out that otherwise this is one-to-one. So what we can say, and this is the result that we have, is something called the birationality of the quadric surface Q with P2. Q and the projective plane are birational, which just means they're isomorphic on dense open subsets. If you throw away some points of the quadric surface, that image inside here is injective, and it surjects onto some open subset of the projective plane. So they are closely related, but they're not the same. If you want to see more precisely what is the relationship, then we have to look at a more complicated and interesting geometric construction called the blowup. Okay, so the quadric surface, which is defined by a quadratic equation in P3, is isomorphic to this P1 cross P1, and it's strongly related to the projective plane. And the best way to see the complete picture of what's going on is to introduce the blowup of this quadric surface. And that's going to be something that contains information both about this quadric surface and the projective plane here. And how is it defined? Okay, we'll define it as follows. What we'll do is we'll look at the blowup at P0 of this Q. So we have picked out this point P0, which is the intersection of these two lines. And we'll look at pairs, P and L. So P is a point of this quadric surface. And what's this L? This is going to be L inside this P3, which contains this point P0. And remember, the lines in P3 which contain P0, they form a projective plane. And that's the projective plane that we have here. So remember, we have a partially defined map from here to here. And the way that works is if you pick a point P that's on this quadric surface inside P3, then you can look at the line containing both P and P0, and that gives you the corresponding point of P2. Okay, so which pairs do we look at? Okay, so this will correspond to a point on the quadric, and this L will correspond to a point on this projective plane. But we only look at the ones where, when we intersect L with this quadric surface here, you get these 2 points P and P0. So it contains the P0, so that's why it corresponds to a line in this projective plane, but it also has to contain this point P here. So L has to contain this P here. So that's a condition that we look at. And let me just say a little bit more about this condition here. Okay, so here you have a line and you're intersecting with a quadric surface which is defined by a quadratic equation. So in this line, when we restrict this quadratic equation to this line, what can happen? Well, the only possible terms you can get are quadratic. So you're solving essentially a quadratic in this line L, but it could be that all those quadratic terms have zero coefficients. So you could actually get the zero equation here, in which case the intersection is the whole line. L intersect Q is the whole line. So in fact, that happens twice. So remember, this line here and this line here lie on the quadric surface. So you have two lines on this quadric surface which go through P0. But if that doesn't happen, what happens? Okay, if that's not the case, then you've got a quadratic equation that you're imposing on this line here. So there should be two solutions. And what this means is that you actually want the intersection here, so the solutions to this, to be P and P0. And actually we want this with multiplicity 2. So if P equals P0, that means that you want this intersection to have be P0 but with multiplicity 2. Okay, so there are the possibilities as to what can happen. Okay, so if you've got this blow up, which I've defined like this, I claim that this is going to be a surface which sits above both this quadric surface and this projective plane here. Okay, so certainly if you're given any point here, you've now got two well-defined maps, one to this quadric surface, because these are pairs P, L, and this P is a point in this quadric surface Q, so you can just map this P, L to P, and you can also map this P, L to L, like that. And how close is this blow up to these two surfaces? That's the question we want to look at here. Okay, so let's have a little think about it. So let's suppose we fix the P down here. If we fix the P down here, how can the L vary? Okay, what sits above a given point P? Well, if your point P was like this one here, okay, which is away from P0, then of course you've got the point L here must contain both P and P0, so it's uniquely determined by those 2 points. So there's only one possible answer for L. So for all of these points P which don't equal P0, this gives you an isomorphism. They're in bijective correspondence, and this map does it for you. The only thing where you have something which is different here from here, this is precisely the time when this map here is not well defined. And that's the case when P equals P0. So when we looked at the case of the conic, the natural choice for what happens when P equals P0, where do you send this point P equals P0 to? Which line? Well, it's going to be the tangent line. And in this case here, the point is you have a surface. So you have lots and lots of tangent lines to this surface. In fact, you have a whole P1 of them. So if you look above the point P0, what you'll find is that there's a whole P1 of lines which sit above it. So there's a whole P1 of L's. And I've drawn that in here like that. There's a whole P1 of L's. Okay, so all of those different tangent lines, they'll correspond to points inside the projective plane, and they'll be these ones here. And in fact, it's of course just the image of this line inside here. So we now kind of see how this relationship works. Okay, the easiest way to see this is using this surface here. Okay, so what's the map that goes from here? Well, most of the time this will be in bijective correspondence. It's just over the point P0 where we've replaced it with a projective line, and that's why it's called blowup, because it expanded this point to a whole projective line. Okay, so when you come back down, it's just the usual map. Okay, so if you go around like this, where it's well defined, it's just the usual map. This is not well defined precisely at this point P equals P0, because there's no unique tangent line you can associate at P0. But what happens is if you look at this multi-valued function here, where going back up, you replace this with this whole projective line, then it does become, going down from here to here, it does become a well-defined map. So the other thing that you see is that this map, it's partially defined, but the other interesting feature is that it's no longer injective, as in the case of the conics. And that's also captured in this picture here. So this line here, what does it correspond to upstairs here? Okay, this will correspond to, except for this point here, if you look away from that point, it will be all the points on this line here, other than the point that intersects this black line here. So these are the points that get contracted in this map. So down here, they also get contracted. So this purple line will get contracted to a single point. And similarly, this purple line here will get contracted to a single point. So now we have a complete picture of what's going on using two properly defined maps which are defined everywhere. And this shows the precise relationship between quadric surfaces and the projective plane. And also suggests that when you study the projective geometry of surfaces, the theory gets much, much more interesting than in the case of curves. I hope you enjoyed this adventure in pure mathematics.